Hey guys, sorry I'm not here today, but we're going to go ahead and move on with what we were talking about in the class. All right, so up to this point we've talked about energy, and you know, at least from 8th grade, you should know that energy is conserved, and that just means that everything that we have today, all kinds of energy that we have today, arose from another kind of energy in the past. Okay, so the gasoline is a form of chemical energy that we have put in our cars, and that arose because gasoline is a fossil fuel, and it came about because there were dinosaurs millions of years ago roaming around, and they fell down and died, and throughout the years of heat and pressure, they became a fossil fuel. And that fossil fuel then became converted, so the energy that they had, as far as the food they ate, became the energy that we power our vehicles with. So energy is conserved. It says that mechanical energy is the sum of all of our kinetic energy and all other forms of potential energy. We also know that the conservation of energy says that energy is neither created nor destroyed, but we can transform it from one kind to another. Our total amount remains constant. So that's just saying here that our mechanical energy, the sum of all of our energies, equals our kinetic energy plus our potential energy, and that's constant throughout this, through before and through after. So let's see. We know that our initial mechanical energy equals our final mechanical energy. So if we take a look here at our system, we've got this weight being held, and because it has a height, it has a potential energy. If I were to cut this string, then it would fall, and all that potential energy would be converted into kinetic energy. So 100% of this potential energy would become 100% of the kinetic energy down here. Okay, and we'll show you what that means. So we know the work done on an object equals the change in kinetic energy plus our change in potential energy plus the work that's done due to friction. It's actually lost due to friction. It becomes heat. So I drop this down. It compresses this, so it has potential energy here. Potential energy gets converted into kinetic energy. As it strikes this plate, it pushes these down, and these particles start moving faster together, and they move faster and faster as they get more compressed. And this will lose energy due to friction. So some of this energy will be converted due to my cylinder here and friction. If we look at our rock, if I hold the rock up in the air, it's got all potential energy because it has only height. As I drop it, since it has half height here, it's going to have half the amount of potential energy that it does. So where does the other half go? It gets converted into kinetic energy because we speed up. So the longer it falls, the faster it's going to be moving. So by the time we get here, we have a height of 0, and we're at our fastest point. If we take a look here at our roller coaster, we see that as we start, we have all, wait till we get back, but as we go throughout the motion here, we see that we have differing levels of potential and kinetic energy. At our highest point is we're going to be moving the slowest, so we'll have only potential energy at our highest point. At our lowest point, we'll be moving the fastest. So at all of our low points, we're going to have the most kinetic energy. But throughout the entire motion of the cart, its potential energy plus its kinetic energy is going to equal the total energy that it has in the system, 100. All right, so here we go. We're going to jump into our first problem in our yellow books on page on page 121, I believe 121. So we have an 8 Newton force. An 8 Newton force. Let's go ahead and get our pointer here. An 8 Newton force pushing a 5 kilogram ball on a horizontal table for 3 meters. Okay, so we have a distance of 3 meters. We've got a mass of 0.5, so 0.5 kilograms, and a force of 8 newtons. So we got an 8 Newton force pushing a 5 kilogram ball on a horizontal table for 3 meters, and it starts from rest. Okay, so if there's no friction, what's our final kinetic energy of the ball? We know that initially we're at rest. So this rest tells us that we don't have any kinetic energy at the beginning, right? So our kinetic energy initially is going to equal 0. right? But we do have kinetic energy at the end, and what does that equal? So we know that we had to do work to our system, so we push the ball, so work equals our change in kinetic energy. And we know that our initial kinetic energy is 0. So our change in kinetic energy is going to be only the energy that we have at the end. So the work we do, we know, is equal to our force times our distance, and that equals our final kinetic energy, Ke. So our final kinetic energy equals our force times our distance. And we plug it in, and we see that our force is 8 newtons, and our distance is 3 meters. So times, actually let's just put it in parentheses, 8 newtons times 3 meters will give us a final kinetic energy of 24 joules. So we have a final kinetic energy of 24 joules. And that's as simple as that problem is. So we know that we know that we have to do work in order to get the object to move, so that's how we find it out. Work energy theorem. Good job, us. So once again, we see that in order for it to move up this ramp, that we have to have a work done in the system. In this case, gravity is what does the work. But anyway, so we'll keep moving forward now. So as our coaster loses height, we notice that we have a high potential energy. We have higher potential energy because we start off higher, and our low kinetic energy because we start off moving slow. So as we speed up down the ramp, our kinetic energy is going to increase, but as our height decreases, our potential energy is going to decrease. So here I have 100% potential energy, and here I have 100% circle that a little better. Kinetic energy. Okay? And over here, since we have a different height, we're going to have differing amounts. Okay? So what we do know, we don't know the amounts specifically, but we do know that the percentage is going to be, you're going to add them together. So let's say we have 25% PE and 75% Ke. So we do know that they still equal up to the same amount. All right, so here we go. So we've got ourselves a 150 kilogram roller coaster starting at the top of a hill on a track. So it starts up here, and it has 37 meters of height. So we know this height is 37. So height equals 37 meters. And we know it's got a mass of 150 kilograms. Okay, so what kind of energy do we have right here at the top of our hill? We know that we're not moving at the top of the hill, so the only kind of energy that we have is an initial potential energy. And that's it. That's all this is asking. It asks for what type of energy. It doesn't ask for how much. And the type of energy we have is initial potential. So that's our answer right there. Okay. So what's our energy present at point A? So at point A over here, what kind of energy do we have? So as we move down the ramp, we know that we have that our potential energy is getting converted into kinetic energy, and at point A we have only kinetic energy. So it's the kinetic energy at point A. That's the only kind of energy we have. So we need to find the speed of our car at point A. So how do we find speed? We know that our total energy in the system is constant. So the mechanical energy initially equals our mechanical energy finally. Mechanical energy is Ke plus Pe, and that equals the same on both sides, okay? But we know that we're talking about final if we're over here on the final side. Okay, so we've got our Ke plus our Pe, and how do we find Ke? Or we know that we're at the top, we don't have any kinetic energy, so all we have is potential, and it equals mass times gravity times height. And our kinetic energy here, we know that we have 0 height, so we are getting rid of our potential energy, and we have kinetic energy of 1/2 mv squared. So, that look a little better. So our mass times gravity times height equals 1/2 mv squared. And that's our velocity at point A. So in order for us to solve for our velocity, we have to simplify. So first thing we do is multiply by 2. So we get 2 mgh equals mv squared. Then we divide both sides by m. Masses cancel, and we end up getting 2gh equals v squared. In order for us to find v, we take the square root. 2 times g times h, and h is our height, if we can read that. Sorry about the little scribbly. So our velocity equals the square root of 2 times 9.8 times 37. So let's just say 10. So the square root of 2 times 10 times 37. So what is that? So 370 times 2. So our velocity is the square root of 740, which is oh, change color there. Which is 27.2 meters per second. So that's how fast we're moving. Well done, us. Okay, we move through this. 27.2. Good job. So what kind of energy do we have present at point B? So now we're looking at point B. So we're not on the ground, and but we're still moving. So we have potential and kinetic at this point. Freezing up a little bit here. Okay, so now we're asked what the energy is present at point B. What is the energy present at point B? So we notice we're halfway up, so we have both kinetic and potential energy. Okay, good job. And now we're asked to find the speed of the car at point B. Speed of the car at point B, pretty simple problem. May not seem like it, but here we go. So we're looking at point B. We know that at point B we have a height of 8 meters and an initial height of 37 meters. Back to my pointer here. I'll point pin. So we're going to start off where let's see. So we know that we have what kind of energy? We have at point B, potential plus kinetic energy. So we know we start off at this point. Initially, we have potential energy. Then here we have both potential and kinetic. So in order for us to solve, our initial potential energy is mass times gravity times height. And that equals our potential energy at point B, mass times gravity times height B, plus 1/2 mv squared, because that's how we find v at B. So because that's how we find our kinetic energy. So algebraically, if we take a look at this, I'm asked to solve for the velocity, right? I want to know how fast it's going. So I'm looking for B, this one right, v at B. So first thing I want to do is I want to move this whole guy over because it's not relevant, so we subtract. So we get mgh initial minus mgh b, and that equals 1/2 mv squared. So we've moved it over, and now we've got v alone over here almost. So let's divide both sides by m. And as I do that, I notice that my masses cancel. And it's no longer relevant in the problem, so I get gravity times height 1 minus gravity times height b, and that'll equal 1/2 my velocity squared. So algebraically, I go 2g times height 1, height initial minus height at point B, and that equals v squared. So v equals the square root of all that. 2g height 1 minus height b. Close the bracket. Plug our numbers in, and we end up getting v equals the square root of 568.4, or v equals 23.8 meters per second. So that's how we do it, guys. That's what's done. And we need to go ahead and continue solving. So good luck, and now what you're going to do is continue the work in your yellow book. All right, thanks a lot.